we are now going to work on connecting electric field to electric potential. And at this point, we actually have four different quantities we've learned about: electric potential energy, electric potential, force from electrostatics, and then the electric field. I really like this table because it lets you start to see what's going on between these. So everywhere in space are these two. So that isn't just one specific situation, but your field exists everywhere, your potential exists everywhere. When this acts locally, that basically involves a specific charge. So that's your probe charge or your test charge. So when we have potential energy, we have our sources and we have some sort of object that is interacting with the sources. Same with the force. We have our sources and then we have what the force is acting on. So then we can think about energy with electric potential and potential energy, or we can think about force with force and electric field. But there's a few other things that are interesting here, specifically about the parallel in how these are mathematically related. If you have electric field and you want to get to force, you multiply by Q, where that Q is the specific thing that is happening locally. Note that it's the same thing going from electric potential to potential energy. You multiply by Q to get that. So now think about what you do to actually go from force to potential energy. Now, we talked about this in terms of work, and so it's basically the negative integral of force, and then you have, and this is again to go from force to potential energy. So one of the ways of writing it is that you have this dot product of force ds, that's a line integral. That's really just work, and depending on which force we're usually using the force acting on the object, so it's negative. So that's how we go from force to potential. Again, that was covered a couple of videos ago, but we thought about this as work. So now, what if we want to go from electric field to potential? Now, if I was to just make a guess, I would say, hey, maybe it's the same thing. Maybe it's negative the integral of our electric field dotted with whatever path we're going to go over. And maybe that is how we go from electric field to electric potential. And in fact, that's exactly what it's going to be. So not only do we have these four different concepts that you can think of in terms of energy or force, locally or everywhere, but in fact there's a parallel in how you go between them mathematically. So the definition is that the change in electric potential is going to be this path integral of our electric field. And we're going to look at some specific cases of this. I know that path integrals aren't necessarily something you've done a lot, depending on your mathematical background. So as long as you're thinking about one component of the electric field, say we're using S here, that could be the X direction or the Y direction, as long as you pick the same direction to integrate over, this will work. We're normally going to work with some fairly simple situations, but in general, this is coming from a path integral, but we can think about it as one dimension as long as the electric field direction is the same as our integration direction. So briefly, what does this look like? Well, if I have an electric field, in this case, note that my electric field is not uniform in space. This electric field is actually linearly changing in space. That I then said, well, what was my potential difference along space? You would integrate that. The integral of a straight line, not a horizontal line, but a linear line, is going to be a parabola. And because there is this minus sign, that means that your potential is decreasing. So how can you actually think about this minus sign? Think about this electric field that is getting stronger and stronger and stronger, but is acting in the positive direction, right? Because these are positive, and note that this is X, this electric field is acting in the positive X hat direction. So if I dropped a positive charge into this field, which way is it going to go? Well, it's going to go in my positive x hat direction just based on the field, right? And the forces that are generated. Well, think about your potential. If you drop a positive charge here, you expect it to quote unquote roll downhill, go towards lower potential. Well, this isn't literally a two-dimensional picture. This is one-dimensional, so that's also going to be in the positive x hat direction. So that's one way to think about this minus sign. It means that the electric field is pushing it downhill. So that's what that integral is going to do for you. So tactics. How do we actually go about finding the potential from the electric field? Well, in general, draw a picture. And we're going to do a quick example of this after this. So if you actually know the electric field, that's how we're going to do this. Obviously, we have some different ways of determining the electric potential directly. So this is assuming that we have some complicated scenario, identify the points, defined in a general coordinate system, but call this position F. So this is our final position. Then we need our 0 point, which is normally going to be at infinity, but not always, which is our initial position. So we're integrating from infinity, or whatever your 0 point is, to your new point. We need a coordinate axis from initial to final, so from infinity to whatever, and that is one direction. And in general, that should be the direction that is aligned with our electric field. And then you integrate. So what does this look like? Let's look at the, this should have been an S, sorry about that. Let's look at just the potential from a point charge. So mistakes here, don't worry too much about that. And we're going to say that our change in potential is our potential at a given distance r. Note that that is here. And so this is the point that we're trying to find it at. We're going to set infinity to be where our 0 potential is. And we are just doing this entire problem in the radial direction. So initially this says S, but it's going to say R. So we need to know what our electric field is. And again, this was a mistake up here. And that electric field is something that we know for a point charge, it goes as Q over R squared with that 1 over 4 pi epsilon naught in front of it. In this case, we're calling it S. We're calling it a general direction, but you could call it R. There's no harm in that. When we finally go to do our integration, we're just plugging this in for our quantity here. Note that we did get rid of this minus sign by flipping the limits of our integration. So we go from R to infinity, we pull out that Q and 4 pi epsilon naught because those are constants, so we're now integrating ds over s squared from R to infinity. So we do get a -1, but note that when you plug in infinity, you get 0, and the lower limit was R, which will cancel with that minus sign. That then leaves us with the potential of R from a point charge, and we already found this. So this wasn't to actually give you any new information. We already knew the answer. But now you can see how starting with the electric field, and again, this S direction here is just going to be R in this problem, we can get back potential. So we really can go back and forth between these two quantities just by doing integration, or as we're going to see soon, taking a derivative.